And recording is rolling. So we're on a Tuesday. You guys just watched a bunch of Paul Hewitt demos related to Newton's Laws of Motion, which you can also access on Google Classroom. They've been there since first week of school. Top scientists for kinematic motion. When you guys walked in, I showed you guys here's my list of top scientists for kinematic quiz. Your name's on here. You did really awesome. Got some owls. You did super awesome. Awesome job there. Did I get you guys your textbook puzzles already? Did I tell you guys they're clipped to the right side of your desk? Okay. Yeah, okay, so you guys got those, right? So they look like these. We'll spend some days in the future solving some of those. And of course, you guys also know that the problems that I assigned to you guys are off that page, right? And just to remind you guys, I told you guys this yesterday, there's a regular homework, so 5 problems from chapter 4, 5 from chapter 5, that I should cover at least these in class with some very similar type ones in class, so as long as you're following along, then it shouldn't be a big deal. But there's also a bonus homework that by default, everybody starts off with an exempt grade, so if you never touch it, that's okay, it's not gonna hurt you. But if you do it, you get some extra points. Just more problems on that page. So how much independent practice do you want? How much do you wanna, how well do you wanna learn physics, right? I mean, the whole point of homework is to give you guys independent practice so you have can understand the stuff better. I want to take up most of the rest of the class to debrief that spring scales lab that you guys did last class, but maybe we should actually do this next bullet point for first, and everything below this blue line we're going to have to save for another day. So, okay. When we talk about forces, remember, force is just a push or a pull. It's measured in newtons, and you guys got your hands on these spring scales yesterday to see that, right? We're also going to be looking at Newton's laws of motion. So what are the laws that govern motion? How do things move? So a recap of what you just saw in those Paul Hewitt demos, for example. You saw a law of inertia. Object at rest will stay at rest unless there's an outside force acting on it. And an object in motion will maintain its velocity. That's to say both its speed and direction of motion. Again, unless there's some kind of outside force. Classic example that goes back to the first week of this class. I asked you guys, what's keeping the Voyager spacecraft going? It's been going since the 1970s. Did it have like 50 years of fuel on it? No, it doesn't need fuel to keep going, right? Once it's in motion, there's no reason for it to like slow down. There's no outside force on it; it's just going. Right? How about your in a car, right? You guys remember another classic example? You're a passenger in a car. Can you feel how fast the car is going? No, you can't feel speeds. That goes sort of hand in hand with this. What you can feel are accelerations, like hitting the gas pedal, hitting the brake, also turning the steering wheel, change your direction motion. We're going to save that for the future, though, so that would be a future topic. Second law of motion looks at acceleration from a different point of view. See, like you guys have been working with acceleration in your kinematic motion. So for the last few weeks, you guys know acceleration is just a rate change of motion. It's a rate change of velocity, I should say. Okay? But we never quite addressed like what would cause something to accelerate, because you guys know from the first law of motion now that nothing wants to accelerate unless there's a force on it. And the second law of motion quantifies that. Now, I think the best version of the second law of motion is this version right here, the fraction version. An acceleration is caused by a net force acting on a mass. Notice I went out of the way to put the subscript net on this, because there could be multiple forces on an object. Like you guys remember the problem of the bunch of bananas and all the monkeys were pulling on the bananas in different directions, isn't that? But there was some resulting net force. Or did I give you guys a problem with the donkey and like people pulling a donkey? Yeah, we did do that. Okay, so same idea. There was some net force that resulted from those individual forces. Once you divide by the mass of the object, you'll know how much it accelerates. Now, it's common to rearrange this algebraically and just say F equals ma, but so you'll have time to see this, but I like to think of it as this fraction. Okay. Then there's Newton's third law of motion. Now, this one says for every force, there's an equal and opposite reactive force. We're really looking at force pairs between two interacting objects. Say if there's a force on object A by object B, there must be an exactly equal and opposite reactive force on object B by object A. This is one of those laws that everybody can say, like everybody's memorized words, but intuitively it's maybe a little bit harder to digest. You know what? Since I got these posters out, let's take a look at how these, at least this one. This is actually a really good third law example. So like this, is the earth pulling you down with some force called the weight? Oh, yeah, go ahead.
What equations should we memorize for this chapter?
Yeah, so what are some, the questions, what are some good equations for this chapter? Let's see if I can dig up here. Okay. On the very first day of school, I gave you guys some pages that are also on Google Classroom, if you need to go back and reprint them out. And we're on this right here. So we've done linear motion, we've done projectile motion, that's all kinematic. Now we're on to Newton's laws of motion. So there's Newton's laws right there. Here's some equations right here. Those are some handy ones. And hey, look, this is a free body diagram. This is one of the new posters too, isn't it? Okay, so we've got F equals ma, right? Newton's second law of motion. We'll eventually talk about friction, tension in an elevator cable. I'll talk about springs a little bit, but we're gonna work our way there. Okay, so that's there. Yeah, so I would recommend those. Yeah, there you go. Okay. That's aside. Right, so you've got some weight that the Earth is pulling you down. Right, now that has to do with the factors like what's the size of the Earth and whatnot. I'm gonna write weight as mg. That's mass times would be free fall gravity. I'll show you why. You guys remember the Paul Hewitt story with the two kids on the island in the Hershey bar? And they were noticing that, they had different perspectives on what eventually came together as Newton's second law of motion. Okay? So two objects, we got a light object and a heavy object. Which one's gonna hit the ground first? This is the Galilei experiment. You know that they'll accelerate the same. So they have the same free fall gravity. Actually, that free fall gravity is a type of acceleration. So I'm gonna take this Newton's second law of motion and modify this a bit. Say, force would be weight in the case of free fall gravity. So weight is what's providing the force. And that has to do with, well, what's the size of the Earth, whatnot. That's a future topic. So for now, we'll just call it weight. Okay? And then your mass, well, that's just your mass, which is the amount of matter that you have. That's kind of a chemistry way of thinking of it. And in this class, we're thinking that represents how much inertia, right? The more mass, the more inertia. Like this has very little mass, very little, it's very easy to achieve, hardly any inertia. This right here, hard to get it to change the state of motion. It has so much mass. And if I take this bottom version is the top version. You guys see the same thing? Okay. Now I rearrange it algebraically, just cross multiply at the end. You guys see that I can get weight is equal to mg. Okay. So all over this class, next few weeks, I'm going to just write mg and use that to represent the gravity pull from a planet, including this one right here. Okay. Now, is the Earth pulling you down? Obviously it is. Are you pulling up on the Earth? Yes. But which force is bigger? Or are they the same force? For every force, there's an equal and opposite reactive force. You and the Earth are actually two objects in providing a force pair to each other with exactly the same force. But why different effects? Like why would you free fall down, but the Earth barely budges? Well, because of entirely different masses. Okay? The Earth is so massive, it's you can treat it mathematically as infinitely massive. So where was I? Oh yeah, we were looking at Newton's laws. Okay, actually, you know what, we wrap that up. Let's switch over to Spring Scales Lab. Spring Scales Lab. So yesterday, you guys got your hands on these lab weights and these springs, and I gave you guys this page, which really had like 10 mini labs on it. And the idea was this was supposed to be an exploratory lab, kind of like a structured sandbox. So I want to go over with you guys what some ideal answers could have been to all these questions and work this out. Okay, so the first one, just pick different weights. So say I got, let's do 100 grams, 200 grams, 500 grams, and 1,000 grams, which is also called 1 kilogram. Okay. What if I pick these four masses? So the masses in kilograms would have gone 0.1, 0.10, that's 100 grams, right? 0.1 kilograms. Okay. This guy, 200 grams, that's 0.2 kilograms. This guy is 0.5 kilograms, half a kilogram, 0.5, half a kilogram. And then 1,000 grams is exactly 1 kilogram. Okay. Now, you throw these on scales, say how much does it stretch? The more it weighs, more force, more it'll stretch, and then it'll reach you higher number of newtons. You should have gotten about 1 Newton here, about 2 Newtons here, and 5 Newtons and 10 Newtons. Okay. So 1 kilogram mass at the surface of Earth weighs about 10 Newtons. More accurately, it's actually 9.8, but these spring scales only have so much accuracy anyway, so and precision. So call that 10. And just to cut to the chase here, increasing mass in kilograms, increasing force in newtons, you should have gotten a direct relationship. Okay. Where the slope of this line, hey, see who's been following real close with what I just told you guys. What is the slope of that line? It is. You guys remember these notes from a few minutes ago? Weight divided by mass. That would be free fall gravity, wouldn't it? It would be about 9.8 or 10 meters per second squared. At this second manual lab, I want you guys to take just one single lab weight over and over, maybe, for example, 1 kilogram, and take a couple of spring scales and shift the weight between, kind of like if you were to balance on 2 feet and then you shifted your weight to one leg and then the other leg, except this is a tension example instead of compression, but same idea. Okay. So you could split it like 5 and 5 newtons. This would be newtons, for a total of 10 newtons if you're dealing with this lab weight right here, right? 10 newtons, or 1 kilogram of mass weighs 10 newtons on the surface of Earth, like that. So that would read 5 and 5. But you know what you could do is you could shift the weight a little bit. So you could put more on one than the other. It could be like 6 and 4, or it could be 7 and 3, or it could be 1 and 9. But you see the rule is that they always have to add up to 10 newtons. I can show that with what's called a free body diagram. Let me break out let's go with a red pen to this. Okay. So if I look at where everything's hooked together right here, if you're holding it at rest, then it's definitely not accelerating. It would be in what's called equilibrium, so all the forces should balance out. There would be 10 newtons pulling down right here, 10 newtons of force due to this 1 kilogram. But then what's holding it up are these 2 spring scales. Let me pick maybe this row right here. It might be something like this. Maybe I've got 7 newtons pulled up from this one, 7 newtons. And then this other one's only pulling up with like 3 newtons of force. 3 newtons. And then the 7 and 3 have to add up to 10, something like that. And then if you graph this, what if the graph looks like? Well, could go up to 10 newtons on each one. Just be, of course, in newtons. Or you could have like 5 and 5. You could put all the weight on one or the other, or if you had split like 7 and 3, it might be, there's about 7 and 3 right there. Okay. What you should see, ultimately, is that all these points lie on a straight line like that. This next one, we're going to take this into 2 dimensions. So it picks up from the last one. Say, okay, well, we're starting with basically 2 spring scales holding it. Okay. Then what if you start to spread these out and make like a Y pattern, and then make it closer and closer to a T shape? What's going to happen? The angle that I specified is the angle of each top spring with respect to the vertical. Okay. You guys see I labeled that right here on the slash diagram. Okay. So it starts out with 0 degrees. That's just everything straight vertical. I'm going to say you picked up 1 kilogram mass again, 1 kilogram on all these. So just the same mass over. That would weigh 10 newtons. So the force on the bottom spring should have been 10 newtons. And that should have been the same regardless of how the top 2 springs were oriented. So I could pick different angles, say 30, 60, 80, whatever. And the bottom spring should always read 10 newtons regardless. You should have seen that. But what about the top springs? Now, top springs would change. Now, if everything is just straight vertical like this, like the first scenario, well, you know that already from this one. It could split 5 and 5. And I probably didn't type this the most scientific way. It's the force of each top spring. Just gave you guys 1 box, but maybe ideally I should have said measure the left one and also the right one. But if everything's symmetrical, if you just keep everything symmetrical, then it should have been about 5 newtons each, right? 5 on the left, 5 on the right, okay, for the scenario. But then once you start to spread this out, something kind of interesting happens. You should see the spring scale readings increase a little bit, okay? And then increase a little bit more. Okay? In fact, I know the number I just wrote actually is an exact correct number for a 60-degree angle, for this angle to be 60 degrees. I know that this box should be exactly 10 newtons for each top spring. And I'll show you guys why. So you guys know the scenario. There's a weight hanging down, there's a spring scale holding up, and there's 2 above that are like spreading out into like a Y shape. Okay? But I want to strip this down and just look at the forces. So here's where everything's held together. Okay? I'm going to draw what's called a free body diagram. Free body diagram. We'll do lots of these tomorrow. Commonly abbreviated FBD because it's just a diagram that shows all the forces labeled. So we've got 10 newtons pulled straight down. I'm gonna switch to red for this. Yeah. No. Purple. That's what I'm doing. So 10 newtons straight down. And then, so what if you held the top two at, well, I'll label the angle. I'll show you guys where this is going. Say something about, try to get this as close as I can. I think that looks pretty good. Probably about what I'm looking for. Okay. Where this angle right here is 60 degrees. Okay. You guys see that? Now if that angle is 60 degrees from the vertical, isn't this one on the left side also 60 degrees from the vertical? Everything's symmetrical. You see that? Wouldn't that make 120 degrees total between those two? Hey, guys, how many degrees in a circle? 360. What's 360 divided by 3? It's 120. That means that this angle is 120 degrees. This angle is 120 degrees. Time out. Hello, Mr. Griffin. Yep, I'll send him down. Ernie, they're looking for you for a checkout. I'm going to send you to attendance. This is pass, system, destination, attendance. All right, so I'm recording this. I'll throw it on Classroom later. So, see you tomorrow. Have a good day. All right. So what I just showed you guys, if this is 120, 120, 120, you guys see how it's symmetrical anyway? Right? Now, even though this is a gravity force pulling down, you can say, well, regardless of what kind of force it is, that's gravity, that's tension, whatever, I could just, no matter how you look at this, if it's symmetrical, isn't this, well, symmetrical no matter what angle? It's like an equilateral triangle sort of deal, isn't it? So even from that point, you already know, okay, well, this must be 10 newtons here. This must be 10 newtons pulling that way. Sure. Sure. Yeah, and that's why I do that for that angle. That has to be also 10 newtons. Okay. But I want to go one layer deeper with this. And I want you guys from a different point of view why that also has to be the case. Before I even taught you kinematic motion, I showed you guys some stuff about vectors and vector components. So what if I take these two tension vectors that are at these diagonal angles and I split them into components that are aligned with that Cartesian system? Okay? Like the one on the left is pulling kind of up and to the left, and the one on the right is pulling kind of up and to the right. Okay? So here's up and to the left. Here's up and to the right. You guys see that? Oh, look at that. Do you guys see a right triangle right here? A right triangle? Okay. And what's this angle right here? Yeah, you guys do see 30. That's a 30, 60, 90 triangle, isn't it? Same thing on the left side. Oh, and it looks like the hypotenuse of this right triangle is 10 newtons. So, hey, could we do like either 10 sine of 30 degrees to get this leg, or 10 cosine of 60 degrees? Either way you do it, this leg right here is 5 newtons. Whether I do 10 sine of 30 or 10 cosine of 60, it's exactly 5, because sine of 30 or cosine of 60 is exactly a half, which is sine of 30 degrees, exactly a half. Same story here. This is going to be 5 newtons. And oh, here, look from this point of view. If the one top left is pulling overall up 5 newtons exactly upward, and same story on the right, 5 plus 5 balances out with this 10 down, doesn't it? You see that 5 up and 5 up balances with 10 down. Okay. And then for completion, what is 10 cosine of 30? 8.66. So this would be 8.66 newtons to the left, and then 8.66 newtons to the right, which also balances out. So all the forces are balancing both vertically and horizontally, so make it equilibrium. If I could just hold it rest. Okay. Oh, is that what I wanted? Yeah. All right. So yes, that. And then, oh yeah, here's where I'm going with this. Is, well, what if you widen this angle out even more? What if you made it closer and closer to a T shape? Right. It's getting closer to a T. Okay? Could you ever make a perfect T? That's one of the questions I asked you. Could you ever make a perfect T? What's the answer to that question? The answer is no. And you can see it exactly from the answer just stands out from this diagram. Because if you had a perfect T shape, you would have no vertical component to these top two tensions. But you need to have 5 newtons and 5 newtons up to always balance the 10 down, whether it's just straight up, 5 and 5 to balance 10, or if it's some component that's 5 and 5 to balance out this 10. But there always has to be 5 newton components. Is that? What is changing is the overall reading in those spring scales. See, sort of simulate this. I know this is from the side, so I get the idea. But see if there's, see, the more horizontally I pull these things, the more the spring scale ratings are going to go up, 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 up. Right? They're just going to get more and more and more until you max out these springs. Okay? So would have worked even just pulling down the graphic. Right. So what if you did take it up to like a 80 degree, if this is an 80-degree angle, 160 degrees between these two, this force should get pretty big now. I can go calculate, it's probably something in that ballpark. Then if you make a graph, the force of each top spring as a function of this particular spotted angle, well, at 0 degrees, it would have been 5 newtons. Okay, got that. Force in newtons. Okay. But then, see, by the time you get to 60 degrees, it would have doubled all the way to 10. And right there, in the middle, it's probably something like this. Okay. And then 80 degrees gets pretty up here. Okay. You guys see it's going to do something like this. Okay. And the fact that the answer to the second question is no, can the angle ever go to the 90 degrees? Let's say, can you ever make a perfect T-shape? The answer is no. That gives you a hint of what the first question would be. You guys see there's going to be a vertical asymptote right here? And the force would go up towards infinity. That's the answer to this box. It goes infinitely large. Okay. Now that has some interesting engineering and materials consequences. So you guys know right now we're on the second floor of a building. There's a void beneath us, and there's a floor holding us up. So as I'm walking around on the floor, one of the consequences of this in material properties is that there's a little bit of give in the materials. Right? So there has to be some width to the floor beneath us, and when you put a force on, it's gonna take some of that force. We got the chain gang going. Yes, so let's throw in 1 kilogram, 1 kilogram there, 1 kilogram here. And those are pretty big weights for the setup, but you could have done that. You guys see that the bottom scale is only responsible for the weight exactly beneath it? 1 kilogram on Earth weighs about 10 newtons, so would have read that. Now, the middle scale has to hold everything beneath it, which is 2 of these slab weights, which would add up to 20 newtons. And the top scale has to hold everything, which adds up to 30 newtons. So suppose maybe there's some warehouse somewhere with maybe some heavy metal chain link hanging straight down, or chain made links. It's getting old, it's getting rusty, it's been there since many days. Which one's going to break first? One near the top, one near the bottom? It's almost for sure going to be one near the top because that one's holding a lot more weight beneath it. How about the next one? What if you slip in another middle spring scale? Let's just say that 1 kilogram, 1 kilogram, 1 kilogram. Okay, so the bottom one is again only responsible for holding up the 10 newtons beneath it. The top one is responsible for holding everything beneath it, which is all 30 newtons. But what happens in the middle? Well, the force is actually going to split. It's going to split half and half. So there's 2 kilograms or 20 newtons of force, 20 newtons of gravity force beneath it. That's going to split 10 and 10. Okay. Guys good? Okay. Good backside. Elevator weight. So if you're accelerating something up or down, what's that going to look like? Let's break out these posters again. They're on the walls. Which one? Here we go. I got a couple of elevators. Of course, we'll look more at these in coming days, solve some problems. I'll do a bunch of these free body diagrams with you guys tomorrow. You guys see these are free body diagrams, right? You got the dot where this guy's center mass is, and then a couple of forces. So in this elevator on the right, this guy is accelerating upward, and the one on the left is accelerating downward. What are the forces that would be consistent with that? Notice that its weight is the same on each one. mg, weight, right? It's the same, regardless of, and Earth's gravity pull is the same regardless, right? But the elevator itself might be moving up, or I shouldn't just say moving up or down. It would be accelerating up or down, which would cause the force from the floor on him to be different. You know what I should have included on this diagram is him standing on a bathroom scale, because that bathroom scale will actually read what's called the normal force acting on this guy. That's F sub n, normal force. So, talk about that. Well, maybe I'll spell it out now, but we're gonna come back to this idea that or some white paper. When you see this F sub n, that's called the normal force. If you're ever pushing against a surface, it will push against you perpendicular to that surface. That's what the word normal means. It means perpendicular. Actually, a really good example of that is a different poster. It's this one right here. You guys remember the block on the incline? Right? So it's weight pulled straight down. You can break that into components. We're about to add more to that story. And part of the story is that this incline actually pushes back against the block, but it pushes back perpendicular. That's why this normal force is perpendicular to the surface. Okay, so all this stuff will come back, but let's just look at this elevator for now. So this elevator scale is reading what this guy, apparent weight is. And you see how on the one on the right, there's a net force that's upward. The floor is pushing up more than his weight's pulling down. That's going to cause him personally to accelerate upward, of course, along with the elevator. The one on the left, notice his weight is more than the force from the floor. He's in partial free fall. That's accelerating downward. Let me flip my screen real fast, show you guys what this would look like on the inside. Okay, present screen 2. Find this elevator. Here we go. And so this guy is standing on a scale in an elevator. You can see exactly what his weight is, right? So see where that needle's pointing. And then, bam! You see that needle jump up? Right? Because the elevator must have been accelerating upward. Okay, so we know this elevator is moving upward. Firm rest had to jump upward to accelerate upward. But then watch this, right? Oh, do you guys see that needle dip beneath his original weight? Right? That's because the elevator is slowing to a stop. And slowing to a stop means it's actually accelerating upward, even though it's moving up, accelerating downward. So this entire video, the elevator was moving upward, well, starting from rest, right? But it starts accelerating upward to get moving upward. Bam, that's that right there. And then when it slows to a stop, it actually accelerates downward to slow to a stop. Okay. Which brings us back to this lab with the spring scales. Stop sharing my screen. Okay. So when you are accelerating upward, 2 ways to do that. You can pull this up faster, faster, faster. The force will increase. The other way to accelerate upward is to lower it to a stop. And then vice versa for accelerate down. You can, the reading's going to decrease. One way to do that is to lower it faster, faster, kind of like free fall, partial free fall. The other way is actually to lift it and bring it to a stop. This next one is very similar. These two are very, very similar to each other. What if you take the spring scale on top and you jerk it to the left, faster, faster? The rating will go up. What if you move it to the left but slow it to a stop? Well, that would be like accelerating to the right, but this one accelerating down. It should alleviate a little bit of the tension. If you move to the right faster and faster, that would also alleviate some of the tension, partial free fall. Okay? And then what if you move to the right and jerk it to a stop? That would actually make the rating go up because it's accelerating to the left, accelerating to one upward. So these go hand in hand. Friction. I'll do a whole friction lab with you guys, and it's going to be in a couple of parts. And this first part's going to look similar to this. What if you had some different masses? Let's bring in some of these guys. Okay. 100 grams, 200 grams, 500 grams. Okay. You lift them, you get 1 Newton of weight, 2 newtons of weight, 5 newtons of weight, something like that. And then you drag it across the floor, and you get something like, I'm just going to make up some numbers, right? 0.5 newtons, 1 newton, 2.5 newtons, okay? Something like that. So in general, it looks like it's taking more force to lift it rather than drag it. But take a look at these 2 columns. Look at the ratio of those 2 columns over and over. You see that ratio is the same? Okay? The drag force compared to the lift force, 1/2/1, 1/2, 2.5/5. See over and over, it's 0.5. That is a ratio that's called the coefficient of friction. And it's defined as friction force compared to the normal force, but it effectively translates as to also be those numbers. Notice the fact that it's the same over and over. That's a material property. I'll talk more about that in the future. It is possible for that coefficient of friction to be more than 1. In this case, it's 0.5. This divided by this is 0.5 consistently. It's very rare for it to be more than 1, but it could be. If you pushed a car across the pavement and it required more force to push it than it would be to lift it, then that would be a coefficient of friction more than 1. So not impossible, just not likely. What if you spun this in a circle? Okay. You know what? Bell's about to ring, so here's what I do. I'm gonna wrap up the video here in the next about minute. You guys can take off to your next class, and then if you want to see these last two, then just stop this video. So you guys have a good rest of your Tuesday. So for the video, I'm gonna finish this off real fast. Okay. So free body diagram real fast. This guy has a weight pulling straight down. This tension is pulling this way, T, which is responsible for holding this vertically, and also pulling it in with what's called a centripetal force. So that'd be mv squared on r, and then see that the hypotenuse is along its side. Okay.
I have a question. I wasn't here for the live
Oh, yes.
Was your question?
Eventually I gotta get him out first. Right, so that would, we'll talk about centripetal force in the future, but for now, what's important is that this hypotenuse of this right triangle, broken into components, has to be greater than the weight itself. So in general, that's going to be the case. Counterexample, if you swung this vertically, which did not do, thank you for not doing that, but if you had, if you swing vertically kind of slowly, you might actually get the opposite. The weight reading, the spring force reading might be actually a little bit less than weight. And finally, buoyant force, if you dunk this in water, see if it's hanging in air, well, air has maybe a tiny negligible buoyant force, but basically weight and the spring force tension is going to balance out. So it's the same. But what if you dunk it in the water? Then what's going to happen is that there's going to be a little bit of spring force and then a little bit of what's called a buoyant force, which is going to be less. So it's going to work out like that. There'll be a quick free body diagram on that one.